Good morning. I thought I'd talk you through question 16 from Monday's work. It's the first question that was set, so in theory it's the most straightforward one, but by talking through it, hopefully we can iron out some of the little kinks and get the subtle points in that will help you with the later questions. So we're looking at question 16 from page 266. It is a potential divider question, so now that you've looked at that on Monday, you should have this should have made a little bit more sense, although to be honest, following the sort of basic electricity laws, you probably could have got to the answer anyway. But now you know it's a potential divider circuit. So we start off with an LDR is connected in series with a fixed resistor R, a 3.0 volt battery with negligible internal resistance. We now know that's significant, of course. A high resistance voltmeter is connected in parallel across the fixed resistor. So we have got in part A, draw a circuit diagram of this circuit. Nice and straightforward. So we'll start with our, in fact we should actually, it says battery, doesn't it? So we should draw a battery properly. We've got our fixed resistor, an LDR, and then we have, we know that this is 3.0 volts, and we've got our high resistance voltmeter in parallel across the fixed resistor. Lovely. I imagine that it says it's 2 marks. I imagine there's 1 mark for getting this loop correct and 1 mark for maybe having the voltmeter in parallel. I don't know. But that is part A. We move on to part B. Which says on a cloudy day when the light intensity is low, the resistance of the LDR is 1.5 kilo ohms. So we'll pop that in. We've already got a little trap there. We're going to need to remember to turn that into ohms. And the voltmeter reads 0.80 volts. It looks like we're doing this to 2 significant figures, this question. Calculate the PD across the thermistor. There isn't a thermistor. An LDR is connected in series with fixed resistor. Well, that's a mistake. We've got no thymistors. We're using an LDR. So let's just ignore that part of the question. So instead, let's find the PD across the thermistor. This is a really nice example of Kirchhoff's second law, of course, which is that the voltages in one loop are going to add to the EMF of the power source. So we've got 3 volts being given to our circuit. We were already told there was negligible internal resistance, so we don't need to worry about any PD being lost within the battery. 0.8 volts went here, which means that we're still going to have our 2.2 volts across the LDR. Good. I've kept it to 2 sig fig, which is probably, yeah, I'm happy with that. Then part C. Calculate the current flowing through the battery. Okay, so we have got 2 resistors. The current. So what we're going to use here is the fact that the current in a series circuit is the same all the way around the circuit. So the current through the battery is going to be the same as the current through each of these 2 components. Which of them is sensible to use? Well, we know we can use the equation I equals V over R, of course, rearrange Ohm's law. We know V through the fixed resistor, but we don't know the resistance of the fixed resistor, so we can't use that for now. We do, however, know the resistance of the LDR, and we've just calculated the voltage across it, which was 2.2 volts. So if the current through the LDR is equal to 2.2 divided by 1,500, that's going to be the same current all the way around the circuit, which means that our current is 0.0008 amps, or let's call it 0.8 milliamps. Cool. We move on to D, which is to find the value of the resistance of the fixed resistor. So we are now looking for the resistance of this fixed resistor. We know the voltage across it. Our conditions haven't changed in the question, and we've just worked out the current around the circuit. So we're going to do R equals V over I, rearrange Ohm's law again, which gives us the resistance of the resistor is 0.80 over 0.80 times 10 to the minus 3, which is going to give us 1000 ohms. Or let's call it 1 kilo ohm, why not? It's a Wednesday. Cool. We then, I'm going to turn the page, I think. Oh, actually, I'll just start a new page so I can still see my notes. You'll notice I've got a very nice setup of my phone balanced on top of a thermos flask, balanced on top of an upturned drawer to get this angle. That was probably the best thing I've done this morning. E. On a bright sunny day, the resistance of the LDR falls to 150 ohms. State and explain what effect this has on the reading of the voltmeter. Okay, state and explain. So we need to say what happens. Does it increase, decrease, or stay the same? And then why? Well, the fixed resistor, remember, and the LDR were in series. Okay, that's just a little snippet of the circuit we had before. They were in series, which means that if the resistance of the LDR decreases, like it has here, it's actually divided by 10, hasn't it? Then the, and this is staying the same, then the resistance of the whole unit is also going to decrease, because if we've got two resistances in series, one of them decreases, the whole resistance is going to decrease, which means that, what was the question actually saying? What happens to the voltmeter? Well, from the resistance, let's go to the current. We know that the current, if the resistance has decreased, the current is going to increase. And since V equals IR, and we've still got the same battery, oh, sorry, you can't see that. And we, there we go. Oh my goodness. This has not gone as well as I thought. Not the best thing I've done today. I'll just, oh my goodness, let's just put that there. There. V equals IR. If, oh no, I'll just rewrite it. If voltage is staying the same, and the resistance has decreased 10 times, then the current, in order to keep the voltage the same, is going to have to increase 10 times. So our current is increasing by a factor of 10. So if, let's just think this through, the voltmeter is just reading across the fixed resistor. Okay, so we now know what the current's doing through the whole circuit. The current's increasing 10 times, but we now need to look at the voltage over here. The resistance of the fixed resistor, that's what my F is denoting, is staying the same. That's not going to change. We'll assume that the temperature remains constant, and that is equal to the voltage there was before divided by the current there was before. But our new current is twice as big. Oh, sorry, no, it was 10, wasn't it? Is 10 times as big as the old current. Oh my gosh. I2 equals 10 I1. And because our resistor has got the same resistance, we can also say that the resistance of the fixed resistor is equal to the second voltage over the second current. I2 is equal to 10 I1. So to keep this in proportion, we know that V2 must be 10 times V1. So if our resistance of that decreases 10 times, then the voltage is going to increase 10 times. Good. Finally, part F. I've just realised something. The whole thing I was saying about the increases and the decreases stands true, but I'm actually not sure whether reducing this 10 times, that isn't actually changing the whole circuit. Oh, but it doesn't matter because, no, because this isn't constant just across this. Okay, forget I said anything about times 10 or divided by 10, because decreasing this resistance by 10 isn't in fact going to decrease the total resistance by 10, because that voltage isn't going to stay the same. So forget the numbers I put into this, just stick with the increasing, decreasing. So it's still true. In fact, let me just get a different colour pen. That's what happens when I think too much on the spot. Forget this. It is definitely true that if the resistance of this decreases, then the total resistance is going to decrease, which does still mean that the total current increases. And for the fixed resistor, if the total resistance decreases, which means that the current is definitely going to increase, which means that for the fixed resistor, if the current, let's just get rid of all that, if the current is increasing, just for the fixed resistor, the voltage will also increase by the same factor according to this logic. This actually is still correct, but it won't necessarily be by 10 just because this resistance dropped by 10. Okay, that will be dependent on the whole ratio of those two. So forget the 10 thing, but it's definitely true that the voltage across this will increase in the same proportion that the current has increased in the circuit. Okay, right, brilliant. Let's move on to F. State and explain the current flowing through the battery if the resistance of the voltmeter was the same as the resistance of the fixed resistor. Well, what we first need to remember is that to start with, the voltmeter had very, very high resistance. We can assume it's going to be infinite. In a perfect circuit, there'll be zero current going through the voltmeter. So what we've done is effectively gone from a series circuit that just happened to have a voltmeter tagged on to introducing a parallel circuit, because we've now got a voltmeter with a lower internal resistance than it had before. So we've introduced a parallel circuit in effect. We know that if we turn this from a series system into a parallel system, then what we're doing is decreasing the resistance of this part. Okay, this part is decreasing in resistance, which means that the total resistance of the circuit is also going to decrease. If the total resistance is decreasing, then our current will, of course, increase. Let's just look at that a bit more rigorously, because that was kind of waffly. So what we've found is the current through the circuit will increase. That's kind of our answer. But what we need to think about is, does this stand up to sort of a mathematical check? Before we had a resistance here, we knew what that was, but that's kind of doesn't really matter anymore. And what we've done is we've introduced, so before we had 1 over RT was equal to 1 over R plus 1 over what we could consider to be infinite resistance. Okay, and therefore if this is infinite, this 1 divided by infinity is going to be approximately 0. So we can eliminate this part, we can approximate this to be 0. And as you can see, the total resistance of the circuit is now equal to the resistance of just that one resistor. I've kind of ignored the LDR in this case because it's not changing. But what we've got now is that this is non-zero, this component here. So our new 1 over RT is equal to 1 over R plus 1 over R. We've set this as the same, 1 over RT is equal to 2 over R. So we have literally halved our resistance. Let's rearrange this. Bring the RT up. 1 equals 2 RT over R. Can you still see what I'm doing? Yes. Bring the R up. 2 RT equals R. And we've now got that the total resistance is half the resistance that we had before. So by reducing the resistance of the voltmeter, what we've done is bring down our resistance of the circuit to half what it was before. If we half the resistance, we are going to double the current. I won't prove that to you now, but I'm sure you can imagine how that works. So our new current is going to be twice our old current with a little 1 in there. Good. Okay, let me know if any of that didn't make sense and I can talk you through it privately. But yeah, I will have a look at the rest. Yeah, you just need to have a look at the rest of the work that I'm going to set now. Excellent. Bye.